This is the study session on quantitative methods, and this is common probability distributions. Before I get into the slide deck, I want you to think about what a probability distribution might mean or might imply. What we're going to be doing is we're going to be looking at data sets. And those data sets could be rolls of the dice, they could be stock returns, they could be yields on treasury bonds. And what we're going to try to do is figure out, based on that data set, whether or not we can estimate the probability of one specific outcome occurring or a series of outcomes occurring. Common probability distributions. First, LOS asks us to define a probability distribution. So let me give you that definition. Probability distribution of a random variable is a graphical representation of the probabilities of all possible outcomes. So here's a simple example. Let's suppose we roll the dice. We know there are 6 possibilities. So if I put 6 across the horizontal axis on a graph, and I put probabilities on the vertical axis, we know that we have a 1/6 chance of rolling any one of those 6 numbers. So the distribution would be a straight line because each has a probability of occurring of 1/6. Let's take the second part of that LOS, distinguish between discrete and continuous random variables. A discrete random variable takes on a finite number of outcomes. It's an actual number, like rolls of the dice that we just talked about, number of CFA charter holders at any time, number of bond funds in the United States. It's discrete, meaning that you know what that number is and it has some economic meaning. Continuous random variable can take on an infinite number of outcomes, like the return on a share of stock could be 6 or 6.5 or 7 or any number in between. You can just add the decimals there. Look at that last one, 6.412325. And you can go on and on and on. Now, some of those don't have too much economic meaning. Like, I'm not sure what the difference between a 6.412325, 6.25% return and a 6.412325, whatever the next number is. So anyway, remember, continuous random variables can take on an infinite number of outcomes. How about a probability function? A probability function gives the probability of a random variable, like a roll of the dice or a stock return, on taking on a specific value. If it's a discrete variable, we use the notation P parentheses X. For a continuous variable, we use the notation F parentheses X. All right, 2 key properties of a probability function. They've got to be between 0 and 1 because something can't have a negative probability of occurring, and you can't have a probability of occurring greater than 100%. And then the sum of all the probabilities must equal 1, which is what we did back here in the roll of the dice. You know, we had 6 outcomes, and each one had a 1/6 chance. So 1/6 times 6, the 6's cancel, and you're left with 100%. The cumulative distribution function gives the probability that a random variable x, a specific x, is less than or equal to a particular value. So we might want to know what the probability that the return on a share of Amazon is going to be negative, and then that particular value of the lowercase x would be 0. Consider a special dividend, 7 possible year-end values. Now, this is a discrete random variable, and we've identified 7 possibilities, 3, 5, 6, 9, 13, 14, and 15, and so each of those is known as an outcome. And the set of possible outcomes can be expressed just like it is right there. So the dividend, and then open the parentheses, and then put all of those specific dividends inside of the parentheses. What about a cumulative distribution function? Remember, that word cumulative means that we're going to add a bunch of stuff together. All right, so there's the notation that's used. Important inside of the parentheses on the right-hand side of the equal sign, we're looking for the probabilities that are less than or equal to a specified value. Quick example here. Let's suppose we flip a coin 3 times. Notice the slide says a fair coin. I imagine there are unfair coins out there. And so what can happen? Go to the far right column of the tree and you'll see at the top 3 H's, so that's 3 heads, and at the bottom you'll see 3 T's, so that's 3 tails. And so what is the probability that you're going to get after flipping 3 times? It's not going to come up heads. Well, that probability is 1 out of 8. And then 3 heads, that probability is 1 out of 8. So that's the top, the 3 H's, and the bottom, the 3 T's. And then in between, the probability that we get 1 head and 2 tails, or 2 tails and 1 head, those are 3 eighths. So those probabilities after 3 coin flips are 1/8, 3/8, 3/8, and 1/8 to get 0, 1, 2, and 3 heads. Now, to determine that cumulative distribution, all we're going to do is sum those individual probabilities. So even if I go just back to this last slide, we start with 1/8, then we add 3 eighths, that gets us up to a half, right? Then we add 3 eighths, that gets us up to 7 eighths, and then we add the final 8, that gets us up to 8 eighths, which is 100%. So that's what that third row cumulative probability does. We go from 1/8 all the way up to 100%. And there's a good picture of the cumulative distribution. Now let's interpret probabilities for a random variable given a cumulative distribution function. What we're going to do is note the cumulative probability up to and including this specific outcome, and note the probability up to and including the preceding outcome. And so we're just going to take the difference between the two. So let's take a quick example here. Suppose we have a discrete random variable which can take on values of 1 to 4. So there we have down the left-hand side, we can have a 1, we can have a 2, we can have a 3, or we can have a 4. And there are the associated probabilities on the right-hand column, and those are cumulative probabilities. So the first one has a probability of 15, and then 30, and then what is that? 35, and then 20, and that gets us up to 100%, right? So what we're going to do is we're going to say, all right, the cumulative probability that x will take on a value of either 2 or 3 is we're going to first figure out the probability that it takes on 2, and that was that 30 that I just mentioned there. So 15 up to the 40, that's 30. And then the probability that it takes on the value of the 3, we're going to take the 80 minus the 45, and that gets us the 35. And I said that back here in that previous slide. And then we're just going to add the 2 because we want to consider that it takes on the value of either 2 or 3. So back here in the slide, we said we can take the difference to get between those two. And in this example, we talked about how we can add those two. So a value of either 2 or 3 gives us a 65% chance. Go ahead and pause the video if you need to refresh the math behind this. How about a discrete uniform random variable? And this is one for which the probabilities of all possible outcomes are equal. And this is why we put the roll of the dice at the beginning example, because we know from our previous discussion that that has a 16.7% chance of taking on any of the 6 values. Now let's go ahead and define this. The probability then is going to be 1 over k, right? So that was 1 over 6. That got us our 16.7%. The mean is defined as k plus 1 over 2, and the variance is k squared minus 1 over 12. And so those are probably good formulas to know. the LOS doesn't ask you to compute any of those things, but certainly in the definition, to be able to define what a discrete uniform random variable means, having those in your tool bag is probably helpful. Now, you might be thinking, how am I going to use this as a financial analyst? And clearly you're not going to say, oh, a stock has a 1/10 chance of occurring between 1% and 10%. You're not going to do that because stock returns can go way up and they can be negative. But what financial analysts typically do is that they use ranges of numbers that have an equal probability. All right, how about a Bernoulli trial? This is an experiment that has just two outcomes, success or failure. And the term success or failure might seem like they have some economic meaning, like success meaning that stock price goes up and failure meaning that stock price goes down, but they really don't have any interesting meaning. You could have a whole variety of outcomes, and just think of it as success is one possible outcome, failure is another possible outcome. The probability of success is given by that notation that looks like a 0 with a line through it. That's the Greek theta. And the probability of failure then has to be 1 minus theta. Now, the binomial random variable is the number of successes inside of the Bernoulli trials, where the trials are both independent and identical. Now, here's where it gets a little fun. This Bernoulli test, if we're interested in performing this test and determining the probability of a success, remember back here with Bernoulli, we're trying to do two outcomes, success or failure. So if we're going to try to estimate the probability of an outcome, we know that probability of success is theta, and then the probability that any of those Bernoulli random variables can take on one specific random variable is going to be obtained by that formula in blue there at the top. Keeping in mind that notation of the parentheses with the n above the x, that's the formula that we used in the statistical concepts video for combination counting. So you've got the factorials in the numerator and some factorials in the denominator. There's the mean and the variance of the Bernoulli random variable. So let's take a look at an example. Probability that any investment bank will survive a large-scale financial crisis is 80%. What is the probability that at least 11 out of a group of 12 Tier 1 banks affected by a crisis will survive? All right, so think about what we're trying to do here. Probability that at least 11 out of a group of 12. And so we're not trying to figure out how many, which particular bank, but it could be any 11. That's why we call this random variable analysis. All right, so what we're going to do is we're going to, what did we do? We had 12, right? So n is 12, and we were given theta as 0.8. And so there's our notation. We want to know what is the probability of x being either 11 or 12. All right, there's the formula. That second one, and that's just, that's the, whoops, I went the wrong way. That's back here using that blue formula. And so we're going to do the probability that x equals 11 and the probability that x equals 12, and then we're just going to sum those. And the interesting part about this problem is that it's relatively easy because we're doing the 11 and the 12. So when we do the numerate, when we do the exponent, we're going to say 12 minus 11, so we're just raising it to the 1 power, and we're doing 12 minus 12, we're raising it to the 0 power. So this makes the computations just a little bit easier in this particular example. So I will allow you to pause to make certain that you can calculate that. Let me just remind you, go back to this formula right there for that combination counting, and that's going to take the spot of where the parentheses are, the 12 over the 11. So you have to do that twice, and then multiply 0.8 raised to the 11th and 0.8 raised to the 12th, and then you have a simple number there to multiply that. So you ought to be able to come up with that relatively quickly. Go ahead and pause. How about a binomial tree? In the video on statistical concepts, we talked about trees and how important they are. Let me just remind you that we're going to do this exact tree in level 2 when we want to compute the price of a bond that has an embedded option, whether it's a call option or a put option. And so it's probably a good idea to learn this now and to figure out what this tree means and how we can use it to help make decisions. Now, the good news here is that all we have to do in this LOS is construct a tree. So what we're going to do is we're going to start at the bottom and we're going to identify the different nodes. So time equals 0, that's one node. Time equals 1 and 2 and 3. So those are 4 different nodes. And at time period 0, we have the stock price. And so what we're saying here is that the binomial tree tells us that the stock price can follow one of 2 movements, right? That's the bi in the binomial. It can either go up or it can go down. And so that's the notation inside of the box at node number 1, the lowercase u and the lowercase d, the s. And so we're not really multiplying there. We're just saying if the stock price today is 100, if it goes up, maybe it's 110 next year, and if it goes down, maybe it's 92 next year. All right, so envision different stock prices. So once at node 1, the stock price goes up to, what did I say, 110, then, since this is a binomial tree, it could either go up or down again. So it could either go up or it could go down to get to node 2 and to node 3. And let me just point something out to you. Go to node 2 there at time period 2. Look in the middle, the UDS. Notice that you can get to that with 2 paths. You can either go up and down or then down and up. And then out at the final node, you have 3 U's, which means that the stock price goes up and then up and then up. And at the bottom, you have 3 D's, which means the stock price can go down and down and down. And this is known as a binomial tree. We can use these for stock prices. We can use these for bond prices. We're going to use these extensively for interest rates. Now, the U and the D can be defined in terms of their expected price movements. So U, in this case, if it's 1.1, then the stock price will go, and I'll just go up along the top path. If U is 1.1, then if S is 100, then the stock price will go up to 110, and then 121 at time period 2, and then 133.10 at time period 3, and so on. And so the idea behind this binomial tree is to get a pattern of future asset prices. In this case, it's a stock price. And so the cool thing about this is that this model allows the stock price to go up and down. I mean, how cool is that? Of course, it reflects reality. On any given day, stock prices can go up or down. That sounds like random stuff that we're talking about inside of this reading. So the price goes up or down, then it can go up or down and up or down. And what we're going to find out is that sooner or later, we're going to get to the Black-Scholes-Merton option pricing model, and we're going to turn this into a continuous function, and we're going to be able to use this thing to compute the price of a call option. But the good news here at level 1 is this: the LOS just asks us to construct the tree. Now, how about a continuous uniform distribution? And this is defined as a random variable that takes values between a lower limit, and that's noted as lowercase a or alpha, and an upper limit, and that's noted as the lowercase beta or b. And so a couple of things here in the bullet points. So there cannot, since alpha and beta are the lower and upper limits, there cannot be an outcome less than alpha or greater than beta. And there's the corresponding probability density function. It's going to be 1 over the upper limit minus the lower limit. And it's probably a good idea for you to get used to the notation there. there's an uppercase X followed by a little squiggly line and then a U. And that's almost always read as the random variable X has a continuous, that little squiggly line, that's a tilde sign, that means continuous, has a continuous uniform distribution with parameters alpha and beta. And there are some unique properties down there in points 1, 2, and 3. And that's a little bit of a summary of what we did above. Let's take a look at an example. You have been given that y is a random variable that has a continuous uniform distribution with lower and upper bounds of 100 and 300. Calculate the probability that y could be greater than 174 and calculate the probability that y could be greater than 100 and less than 226. So there are two good questions there. And all we're going to do is get out that formula that we had earlier. Let me swing back. There it is in blue. So we're going to use that formula. So we have 1 over 300 minus 100. So each unit interval in this continuous uniform distribution has a probability of 1 over 200, which means that the probability that y is greater than 174. All right, so think about this. You know, you have from 100 to 200, and so what we want to do is figure out the probability that y is greater than 174. So we're going to take the 300 minus the 174 and divide that by the 200, and that gives us 63%. And then coincidentally, since that interval has the same length as the one above, the probability of moving between 100 and 226 is going to be that same 63. How about properties of a normal distribution? A random variable is said to have a normal distribution if its value makes a smooth curve that assumes a bell shape. Now, I don't want to swing all the way back to the very first distribution that we had. Remember, that was with the rolls of the dice, and that was just straight across. It was a straight line. But normal distributions, of course, have lots and lots of data points right around the mean. And as those data points get further and further away from the mean, they occur less frequently. And that's the nature of the bell-shaped curve. We use the notation mu and sigma to stand for the mean and the standard deviation. And there are some distinguishing properties. Random variable has a normal distribution with a mean mu and a variance sigma. It has a symmetric shape, which means skewness is 0. And kurtosis is 3. Remember, kurtosis measures how tall or how flat the curve is around the mean. Kurtosis of 3 is normal kurtosis. More key properties: the mean, the mode, and the medium are all the same number, and they lie directly in the middle. If x and y are normal distributions and you combine those two variables, then the resulting distribution will also be normal. Standard deviation, since it's at the same base level as the mean, can be added and subtracted. Probabilities follow that empirical rule, 68, 95, and 99 rule. And there's the formula for probability that a value lies between A and B. Here's a picture of the normal distribution. This is a standardized normal distribution, actually, because the mean is 0. Notice right in the middle, the meat of the curve is 0. And then we're moving to the left and moving to the right. Notice that's symmetrical. So if you put a mirror right smack dab in the middle, it's the left side is a mirror image of the right side. And what's interesting for financial analysts is to move 1 standard deviation and 2 standard deviations and 3 standard deviations away from the mean. And that's going to be really important. And that takes us back to that 68, 95, and 99. I mean, here's the general empirical rule that 68% of all outcomes fall within one standard deviation of the mean. 95% of all outcomes fall within 2 standard deviations of the mean. And then a little bit more than 99% fall within 3 standard deviations of the mean. That's probably important to remember. The next LOS asks us to determine the probability that a normally distributed random variable lies inside a given interval. So this is what we're going to do. We're going to calculate something called a confidence interval. It's really just an interval. We call it a confidence interval because we're trying to determine with some degree of confidence. You know, like let's take a treasury bond yield for a real simple example. Suppose that yield is 2%. A confidence interval around that 2% is going to be 2% because it's a default risk-free security, meaning that you know that you're going to get 2%. So we can say with 100% confidence, we're going to get 2%. But if that is not a treasury bond, if it's a share of Amazon stock, and we expect to get, let's say, 12% out of Amazon, what's a confidence interval that we can put around that 12% that is reasonable? And what we say is something like, hey, with 95% confidence, I can say that Amazon will return next year between, let's say, a minus 20% and a positive 45% or some number like that. So that's what the confidence interval means. We're going to find a lower bound and an upper bound based on, and it's typically 95% confidence levels. And that allows us to make decisions. Of course, we have clients who might want Amazon in their portfolio, so we present this confidence interval to them and say, hey, look, there's a 95% chance that you're going to either lose 20% or gain 25%, or 45%, and then anywhere in the middle between those two numbers. And then we have a discussion with the client about whether their risk tolerance is able to handle that. Now, of course, we're not going to do that just for every individual stock. We'll do that for portfolios of stocks. All right, some bullet points there. I think I mentioned most of those. Precision or accuracy depends on the width of the interval. I mean, we could do a 5% confidence interval, and we could say, hey, you know what? With 5% confidence, I think Amazon's going to lose between a minus 97% and gain 300% or something like that. Yeah, here's some applications of what I've been saying. So 68% of all observations fall within 1 standard deviation. 50% fall within 2/3 of a standard deviation. That's not too commonly used in the world of finance. We usually go out to 2, and that's why we come up with this 95% confidence interval. Now, normal random variables, they can take on almost any value. So what we like to do in statistics is to standardize them. So a standard normal distribution refers to a normal distribution that has a mean of 0 and a standard deviation of 1. So let me quickly just go back to this graph, and that's what I was saying just a little bit earlier. Notice in the middle, there's the mean of 0, and then standard deviation of 1. So we go out 1, and then we go out 2, then we go out 3, and then we go out 4. And of course, this horizontal axis puts 0.5s in between all of those just for some extra clarity. All right, so let me go back to here. So a normal distribution, standard normal distribution, has a mean of 0 and a standard deviation of 1. What we can do then is we can convert an observed value into the standardization process. So all we're going to do is take the observed value, call that x, subtract the population mean, call that mu, and divide by the standard deviation. And that's our z value. Some people call it a z statistic. Some people call it a z score. Let's take a look at an example. Portfolio has an expected mean return of 8% and a standard deviation of 14%. All right, so here we're getting back to this. We're not going to do a confidence interval, but we're getting back to that sense of how accurate, how confident can we be in that return of 8%. Now, this has risk. Remember, standard deviation measures risk, so the standard deviation is not 0. Standard deviation would only be 0 for treasury bonds when you hold them until maturity. But we want to know what the probability that its return will fall between 11% and 15% if we expect to get 8%. So right off the bat, you ought to think, all right, this probability between 11 and 15 is not going to be a big probability, right? Now, in order to solve this problem, we're going to go back here to that blue formula in the middle. We're going to compute the z value, and then we're going to look that z value up on the z table. And right here, there's just a partial z table, and I'll repeat it on the next slide. But those partial z, the z table is going to give you the actual probability. So let's see what that means. So forget about the table at the top. Let's go ahead and do the formula. So at 15%, we calculate the corresponding z value by taking 15 minus 8 and divided by 14. That gives us 0.5. And then at 11%, we do 11 minus 8 divided by the 14. That gets us 0.21. So those are the z-scores. What we need to do is find those z-scores on the z table. Now, notice the z table has a left-hand a vertical column and a top horizontal column. So those are the z values. So what you do is you run your finger down along the left-hand column to get the first digit, and then over the columns to get the next columns to get the second digit. And so the 0.5 is easy, so we go down to z of 0.5 and we go to the column of 0, 0. So you add 0.5 plus 0.0, and so that probability is 69.15%. And then the probability corresponding to the 11%, run your finger down till you get to 0.2. Run your finger over until you add 0.01. So 0.2 plus 0.01 gives you the 0.21 z value. So that's 58%. And so to get the corresponding value that this security is going to generate a return between 11 and 15%, you just take the difference between those two probabilities. So 69 minus 58, that's about 11%, right? So I was rounding there, and the actual number is 0.1083. Go ahead and pause the video if you need to remind yourself about how to compute those z-scores, or if you need some help with the table. Now remember, this is just a partial table, so at the top it goes all the way over to a 0.09, and all the way down, z goes from 0 all the way down to 3. So this is a big table that you'll probably be given a partial table on the exam. How about the difference between univariate and multivariate? Uni just means one, so that's going to be a one random variable. And multivariate means that we're going to consider a group of related continuous random variables. Now, let's go ahead and ask maybe the first question that's directly related to investments or finance. Let's do Roy's safety first criterion and what this means for shortfall risk. So there's a picture of the bell-shaped curve. There's a beautiful curve. And what we're concerned about is the left-hand tail. Notice in the middle we have the mean. We're calling this the expected return on a portfolio. And so that might be 10% or 15%. What we want to do is we want to know what is our shortfall risk. So if that expected return on the portfolio is, let's just say it's 10%, and we're concerned about our portfolio losing value, that would mean a negative return. So if we go all the way over there to the left, that might be 0. And so shortfall risk might be defined as the probability that our portfolio is going to lose value. Or in this case, notice I have some notation there, it might be that what is the probability that our portfolio will fall below that of the benchmark return. And so that's why in the one bullet point I have will not exceed the benchmark. And this is a great measure of downside risk. Now that shortfall risk is a probability, so because it's to the left of the mean, it's going to be less than 50%. You know, maybe it's 2%, maybe it's 8%, but that 2% or the 8%, it depends entirely on the standard deviation of the portfolio. That's why we spent so much time in the video on in another quantitative methods reading on computing the variance of a 2-asset portfolio. Now, linking this directly to the safety first criterion, when you look at that formula in the middle of the page, your first thought should be of William Sharpe and the Sharpe ratio. And of course, this is related to William Sharpe. But unlike the Sharpe ratio, which subtracted the risk-free rate out of the numerator, we're going to subtract that threshold level. And so back here, that's why we talked about shortfall risk and the downside risk, because we can establish that base over there on the left-hand part of this bell-shaped curve. Maybe it's 0, maybe it's the return on a benchmark, or maybe it's something else. And so that's what we're doing with the safety first ratio. We're going to take the return on the portfolio, expected return on the portfolio, subtract out that threshold return, and then divide by the standard deviation. Once again, standard deviation is our critical measure of risk, and it's extremely important to be able to manage all of these different types of investments. You'll hear me say this on the videos multiple times. What is our goal? Among all of our goals as financial analysts is to identify the risks, quantify the risks, and then manage the risks. And so that's what we're doing here. We're identifying risk, we're calling it total risk, and we're quantifying it using standard deviation. And then we're using all this statistics to help us manage the risk. All right, how about normal and log normal distributions? And so here I'm going to ask you to look on your calculator and find the LN button. And all you're going to really do is turn a normal random variable into a log normal random variable by hitting the LN button. And so sometimes random variables just follow some other kind of distribution, but when you convert them to its log normal form, they follow a normal distribution. And so you can make all the same kind of conclusions that we've made up to this point in the slide deck. Look at the bottom bullet point I have. Stock returns, they tend to follow normal distributions. Not perfect, but probably for the exam's sake, it's probably okay to think of them in terms of a normal distribution. But stock prices follow a log normal distribution. So that's an interesting distinction. I think if you remember that one, that'll probably help you remember how to explain this relationship. All right, how about continuous compounding and discrete compounding? Now, remember when we did our discrete compounding back in the time value of money section of quantitative methods, we took $100. And if the interest rate was 10% and we compounded out over 1 year, we got $110. So that was discrete compounding. But what happens if interest is compounded continuously, like every instant of every day, continuously? Well, what we need to do is be able to convert from effective annual rates and holding period returns back into continuous rates. And so that's what I do here in this quick example. So look in the middle of the page, the blue formula. Let's suppose that we have a continuously compounded rate of 9.531%. How do you convert that into a discrete rate of return? We'll call that the effective annual return. Well, here's where you need the E to the X button on your calculator. So back in this previous slide, I asked you to find the LN button. Now find the E raised to the X button. And so all you do is take the 0.09531 and then hit your E to the X button and subtract 1. And that gives you an effective annual rate of 10%. Now, the flip side of that is, let's go down to the bottom part. If we start with a stock price today and of $100, and we know after 1 year it'll be $110, that holding period return is 10%, right? So that would be the discrete rate of return. But we can convert that discrete rate of return into a continuously compounded rate, and that's where we use the LN button. So we're going to add 1 to the holding period return. 1.1 raised to the 1 power, do the LN, and you'll get the 0.9531. And so this is an important lesson here. Notice that the LN button and the e to the x button, they're kind of like opposites of each other. I mean, they're not really opposites, but think that when you have one thing and you hit the ln or the ex button, you get the other. So you go from discrete compounding to continuously compounding. And so the ln and the ex button, those are valuable buttons to be able to use on an exam when you're asked to go from one to the other. What about Monte Carlo? This is really a fascinating development with the advent of computers. What I want you to do is I want you to think of an Excel spreadsheet. And on that Excel spreadsheet is a big old capital budgeting problem where across the top we have a bunch of years, like maybe 1, 2, 3, 4, 5 years. And what we want to do is we want to compute the operating cash flows. So down the left-hand column, we start with revenues and we take out operating expenses and we take out depreciation and we take out taxes and we do all that stuff. So you have this big old matrix. And at the bottom, you compute the operating cash flows. And then from that, you can do net present value and internal rate of return. Well, what Monte Carlo simulation allows you to do is to write an algorithm in which you change each one of those variables by some reasonable economic number and then recalculate the operating cash flows and then recalculate net present value and then recalculate internal rate of return. And so what you do is you run this model and then you change a variable. And then you run it again and you do this over and over and over and over and over again because clearly you want to be able to determine how the net present value of a project is sensitive to independent changes of all of those random variables. You know, now revenues and expenses, they're probably not random. They're probably dependent on the last year, but you get the sense that if you put this in a random variable framework, you can change one variable and then you can run this hundreds or thousands, maybe even 10,000s of times. It depends on how complex the computer is. And so you do this over and over and over again until you can, here, let's look at some applications. Establish downside risk during the management of assets and liabilities. Boy, that sounds really important. Rather than just taking a confidence interval based on a small sample size, you can do this Monte Carlo and you can do it over and over and over again. You get 10,000 different possible outcomes, and then you can really have a better estimate of shortfall risk. Here's the example I was giving you, project appraisal. That was determining cash flows and how they're affected by different circumstances to be able to compute net present value or internal rate of return, and then simulating profits. I mean, there are all different sorts of ways that you can use Monte Carlo. Now, what are the limitations? I mean, it's not perfect. You know, it provides us with statistical estimates. They're not exact figures. It's fairly complex. And so the software is not cheap. And then when you write the algorithm and you change the variables, like let's suppose we're back on that capital budgeting problem, and we're changing the tax rate. You know, cash flows depend on the tax rate, the corporate tax rate. So suppose we change it from current 21% to 22%, and then 23%, and then 44%, and then 55%. I mean, it's sooner or later, once you get up to 55%. You're going to get some results that don't have any economic meaning. So they can be potentially misleading results. So when you're writing the algorithm, and of course you would never have to do this on the exam, but in explaining Monte Carlo simulation, you need to make sure that the analyst is careful in terms of the ranges over which each of those variables are changed. Now, historical simulation involves the use of the historical record. But Monte Carlo simulation relies on modeling the distribution of risk factors. And so what are those risk factors in our capital budgeting problem? Well, with revenues and expenses, those risk factors depend on the competition, let's say. They depend on maybe government spending. Maybe they depend on the level of interest rates. So you can model those risk factors inside of Monte Carlo that you can't really do using historical simulation. Yeah, Monte Carlo incorporates a wide variety of scenarios. What if the tax rate goes from 20 to 21%? Very expensive. Services of an expert. main advantage of historical simulation is that you are looking back, and so if you can identify those specific risk factors that occurred throughout history, well, then you can use those in the model to help you predict what the future is going to be. Of course, there are some disadvantages. Using history doesn't really necessarily mean that history is going to repeat itself, and outliers can really mess up the data and the interpretation. And it's tough to identify risks for a specific time period. Oh boy, there was another long video. Common probability distributions. Next up, sampling and estimation.